video that we made, we talked about something called a negative half-wave rectifier. It was catching all the negative waves. And then we also talked about how you can combine the negative and positive half-wave rectifier and possibly make something called a full wave rectifier. That way you catch both the cycles of the DC and eliminate that these gaps that you see here. Eliminate that basically. So let's see how it's done. Here is an article I pulled up. It's for the full wave rectifier, and let's see what they have done to achieve that effect. Okay, so this is the diagram of the full wave rectifier. As you can see, that gap that was there in the previous half wave rectifier where there was no current, that's not there anymore, because now effectively you're using two diodes, right? So let's see how they've done this. So this is the transformer we spoke about, and if you see it in the middle, there is like a wire that is connected here, and this resistance that you see is a load. Load can be anything, a bulb, another device, anything. So it's represented by resistance, and you see that it is connected to somewhat at the middle, right? And they have referred to it as the center tap. So why is that center tap needed? Why? How is it helping and all that? We'll come to that. First, how it works is, as they have neatly traced out in the arrows, like here. See, as the current flows through the positive half cycle, then it flows through the first diode. And during the negative half cycle, it reverses like its direction, and it flows like this, right? And it flows through diode 2. So that is pretty obvious to you by now. But here, let's see the center tap. See, center tap is nothing but this is the primary coil of the transformer. This is the secondary coil of the transformer. You don't really need to understand how a transformer works for these purposes, but it's enough for you to know that it's being used to step up or step down the voltage, right? So this secondary coil has been tapped at the center, in the sense that they have taken a wire and connected it at the center, so that this point in the graph that you see there, exactly where the current is reaching a point when it's zero, and then it changes direction. At this point the center tap, it's coinciding, so they have managed to locate it that way, so that you are essentially dividing the transformer coil in half, right? This is one part and this is the other part. So that's what they managed to achieve, and that is helping them divide it so that one diode works in the first half of the cycle and the second diode works in the second half of the cycle. That was the purpose behind tapping it, so that you have two separate circuits, right? So this is how they've explained it further in the article. You can go through that. Just what I told right now, it's been explained here. Okay, and so yeah, that's how they have divided it, so that you have two separate voltages, V1 plus V2, right? That gives you the V total of the transformer. This essentially, that wire is helping you divide the transformer into two halves, right? So this division, can you guess what it's? It's actually a minor. This division that's been done, it's actually giving you a disadvantage. Can you guess what it's happening? The clue is right here. So have a look at this graph, right? Any idea on that? So one of the things that you should keep in mind is the voltage is getting divided. You're giving a total of V total, like a bunch of voltage here, but it's getting divided into V1 and V2. So the output that you're going to get from the transformer, from the full wave rectifier, it's going to be less than what you're giving it, right? So there's definitely going to be some loss, and it's further explained here. So once they're done with this entire explanation, we can go down and scroll. Right. And here's a nice graph explaining diode D1 and D2 plus how they constitute a full total output current. Right. So basically that's how it works. And if you observe this graph again, you see that this is not pure DC. UVDC in the sense voltage remains constant with time, right? You have a flat line that is parallel to x-axis. But here you have something that is called a pulsating DC, as in its value keeps changing with time. It is still unidirectional. It's not changing the direction anymore, but it's very loopy in the sense it's changing direction. So now we need to figure out a way in which you can reduce these loops or these pulses that you don't want it to vary so much. So they came up with a solution, right? And we'll hint towards that, right? That is something called a ripple factor, and this is how they measure it. It's the ratio of Vrms, which is the root mean square voltage, divided by the DC voltage whole square minus 1 towards the square root. Right? There's even a nice derivation on how you get this. So this is the ripple factor, and it tells you how much ripple you get. A ripple in the sense you can just imagine it as the disturbance that you have. These are some parameters that help you compare the full wave rectifier, the half wave rectifier, and the bridge rectifier. I'll cover those separately, but for now you should know that this is significantly lower than what it was for the half wave rectifier. So I will even pull up tables and everything for that, and we can have a detailed discussion on that later. But for now, just be familiar with these terms. Rectifier efficiency. So it's the output power by input power. Output DC power, remember, because it's being converted, and to the input AC power. So it appears to be 81.2%. And here's another term, peak inverse voltage. So this is the maximum, voltage that the diodes can take before it breaks down. So again, there are derivations for this, and how it's arrived at and all that. It's pretty simple. You can go over it in a different video. But for now, it's sufficient for you to know that it's about 2 Vs max for peak inverse voltage. Right? It's 2 times the saturation voltage. Sorry, Vs. Right? That's something. And again, these are terms you can always get back to. Right? And so some of the advantages of the full wave rectifier have been mentioned here. High rectifier efficiency, low power loss, low ripples. But then there is something of a major disadvantage here. High cost. So remember that center tap I spoke about? For winding and all that and tapping it. So that's a major disadvantage here. Getting a center trap transformer, it's expensive, it's bulky and difficult to get hold of and all that. That's a major disadvantage. Also, the peak inverse voltage that I mentioned, it's 2 times Vs max. So that's a lot of voltage, right? I mean that's twice the amount of voltage that you expect to happen. So that's another disadvantage. And let's see, I pull up a Quora thread on this. So we'll just take a look at what they had to say about that. One sec. So the Quora thread that I spoke about, it gave me the following disadvantages. So yeah, let's have high peak inverse voltage, and it's only one half of the transformer secondary voltage. Remember, I hinted at this disadvantage while discussing V total is equal to V1 plus V2, that dividing the voltage of the transformer by 2. So yeah, these are the disadvantages of a full wave rectifier. Now there's a particular video made by this person called Afrotech mods. Like this is the channel. I would highly encourage you to watch this video. It's going to give you the exact idea on how we progress from a half wave rectifier to a full wave rectifier to a bridge rectifier. So what's a bridge rectifier? Why was it needed? We'll come to that now. But I would really encourage you to go through this video. It's very well explained with actual construction on the breadboard and the radio frequency application. So, and even the oscilloscope that you can see here. Oscilloscope is just a device you use to measure waveforms and voltages and things like that. It helps you diagnose the circuit and things. So, yeah, please go through that video. It's going to give you a very good idea. And so now we will discuss why how can we overcome this problem that we have here, right? That this center tap transformer that is there. So we have 2 diodes right now and a very expensive transformer. How do we, change the situation? How do we eliminate this whole center tap business so that, we make it cheaper and less risky? So we'll see that in the next video.